Okay, let's dive right into this explainer and demystify what honestly often feels like a really intimidating math concept, matrices. Like if you've ever stared at a textbook and felt totally overwhelmed by those giant brackets filled with grids of numbers, you are definitely not alone. But today, we're going to break it all down. We'll strip away the complexity and show you exactly how to conquer matrix addition. It is actually a lot simpler than you might think, and we're going to use just 3 simple steps for adding matrices to get there. To really understand how modern systems process massive amounts of data so efficiently, we have to look at the mathematical hero behind the scenes. So before we get into the how, let's think about the why. How do computers render beautiful 3D graphics in a video game? Or how do economists model entire industries? How do huge retail giants track thousands of items across hundreds of stores? Well, they do it by relying on matrices. By mastering this foundational skill today, you're literally learning the language that powers our entire data-driven world. So here is our quick roadmap for today. First, what is a matrix? Second, our 3 steps for adding matrices. Third, the rules of addition. Fourth, we'll meet the zero matrix. And finally, why matrix addition actually matters. Okay, part 1. What is a matrix? Demystifying the grid. Let's start with the absolute basics here, and just remove that intimidation factor right off the bat. The crucial point to remember is that a matrix is simply a way to organize numbers into a neat rectangular grid. That's really it. It's basically just a box of numbers. We organize these numbers into rows, which run left to right, and columns, which run up and down. And each individual number inside this grid, that's called an element or an entry. So when we talk about the size of a matrix, we're literally just counting its rows and columns. Moving on to part 2, the 3 steps for adding matrices, the simple recipe. Now for the really fun part. We're going to focus on these exact 3 steps. Verify dimensions, add corresponding elements, and write the resulting matrix. Seriously, once you memorize this sequence, adding matrices becomes just as straightforward as basic elementary school addition. Let's break down step 1. So step 1 is absolutely vital. Verify dimensions. If your matrices do not have the exact same number of rows and columns, well, I'm sorry, you're out of luck. Addition simply won't work. In linear algebra, this is called having the same order. Basically, if you have a matrix with 2 rows and 2 columns, you can only add it to another matrix that also has 2 rows and 2 columns. You can see a super common mistake right here, where trying to add mismatched matrices makes the calculation completely undefined. Why? Well, because matrix addition is a strict partner system. It's kind of like a middle school dance, right? Nobody wants to be left standing alone without a partner. Every element in the first matrix needs a matching partner in the exact same spot in the second matrix. So if you try to add a 2 by 2 matrix to a 3 by 3 matrix, you're going to have leftover numbers with 0 partners. So always check your dimensions first. Okay, let's move to step 2 and see how this builds. It's just a simple element by element addition. Once you've confirmed that your matrices have matching dimensions, you just pair up the numbers based on their location. So top left goes with top left. Bottom right goes with bottom right. You get the idea. Imagine lining up 2 identical grids side by side, perfectly matching the top left corner to the top left corner. For example, let's say we have matrix A with the numbers 1 and 2 on the top row, and 3 and 4 on the bottom row. Now we want to add that to matrix B, which has 5 and 6 on top and 7 and 8 on the bottom. Since they're both 2 by 2 matrices, we have a total green light to proceed. And now you simply add those corresponding numbers together, just exactly like basic arithmetic. We take the 1 from the top left of matrix A, and we add it to the 5 from the top left of matrix B. Then we grab the 2 from the top right and add it to the 6. We do the exact same thing for the bottom row, 3 plus 7 and 4 plus 8. It is purely about matching up those positions. Finally, step 3 is just writing down the results of those mini addition problems into a brand new grid. Your new matrix is going to be the exact identical size as the ones you started with, meaning if you added 2 2 by 2 matrices, your answer is going to be a 2 by 2 matrix. And there you have it. You've successfully added 2 matrices. Our 1 plus 5 gave us 6 for the top left. Our 2 plus 6 gave us 8 for the top right. Down on the bottom, 3 plus 7 is 10, and 4 plus 8 is 12. So our final resulting matrix, let's go ahead and call it matrix C, is simply 6, 8, 10, 12. Just remember those 3 easy steps. Verify they match, add the corresponding spots, and write it out. All right, part 3, the rules of addition. Good news for math fans. So if you're worried about some bizarre alien rules that you have to memorize from scratch, I actually have some great news for you. Matrix addition behaves just like regular addition. The order in which you add them or how you group them doesn't change the final result at all. This is known as the commutative property. Basically, matrix A plus matrix B is exactly the same as matrix B plus matrix A, because we're just adding individual numbers inside the grid. 1 plus 5 is identical to 5 plus 1. And on top of that, it also has the associative property, meaning if you're adding three matrices together, say A, B, and C, it really doesn't matter if you add A and B first or B and C first. The way you group them won't affect your final grid one bit. Moving on to part 4. Meet the zero matrix, the additive identity. Now let's introduce a very special character in linear algebra. You know how every mathematical operation usually has a concept of nothing? In regular math, it's just the number 0. Well, in the matrix world, we have something super similar. The zero matrix, which is sometimes called the null matrix, is a grid filled entirely with zeros. It's usually denoted by a large O or a bold 0. Just like adding 0 to the number 5 keeps it at 5, the zero matrix serves as the additive identity, meaning if you take literally any matrix and add a zero matrix of the same dimensions to it, you just get your original matrix back. It leaves your data completely unchanged. And this naturally leads us to the inverse property. If you add a matrix to its negative counterpart, which is basically a matrix where you flip the sign of every single number inside, they cancel out perfectly. Every element minus itself equals 0, leaving you with that perfect, empty zero matrix. Finally, part 5, why matrix addition matters in real-world applications. So, you might be thinking, why does any of this matter outside of a math classroom? Well, imagine a giant retail company with massive inventories. Let's say they sell dozens of items across different store locations. They actually use matrix addition to combine the stock data of multiple stores instantly. Instead of adding up items one by one on a calculator, a computer can just view store 1's inventory as a matrix and store 2's inventory as another matrix. Here you can really see how multidimensional data is consolidated seamlessly into one clear, actionable total. By executing those 3 steps for adding matrices, verifying dimensions, adding corresponding elements, and writing the result, the retail software creates a brand new total stocks matrix. This tells management exactly how many pairs of shoes or laptops they have across the entire company in a fraction of a second. It's a total game changer. And beyond retail, these foundational 3 steps power a multitude of advanced fields. When you use photo editing software to blend or enhance an image, the software is actually treating the pixels as a matrix and adding them to apply filters. In economics, experts use matrices to map out how different sectors of an economy interact. And in general data analysis, anytime you have large, complex, multidimensional datasets, matrix addition is exactly how you combine them. So we've seen that adding matrices is as simple as verifying their size, matching up the elements, and writing down the results. But I'm going to leave you with this thought. While addition is friendly, predictable, and commutative, what happens when we try to multiply them? Well, it turns out matrix multiplication breaks these rules entirely. Suddenly order matters, and the steps look completely different. But hey, that is a fascinating topic for another explainer. Keep practicing those 3 steps we went over today, and you'll be more than ready when the time comes.